everybody. My name is Jim Fentner. I am the chair of the Department of Chemical Engineering and the Associate Vice Provost for Research Computing. Super excited to welcome Tess Smidt today to give an eScience seminar. She got her bachelor's degree in physics from MIT. After that, she went to Berkeley, where she earned a master's degree and a PhD in physics. And since 2018, she's held the title of the Alvarez Fellow at Lawrence Berkeley National Lab, which is one of the few named national lab fellowships. So it's a really prestigious honor. She's an accomplished researcher in physics and has been working more recently in the intersection of data science, neural networks, and atomic geometries and calculations. So please join me in welcoming Tess for her seminar. Thank you.
Thank you so much for the introduction, Jim, and also thank you to the eScience Institute for hosting me. I've had a lot of great conversations over the past couple of days on a variety of topics, so much science. It's been super exciting to be here. So today I'm going to be talking about some work that I've done and am doing sort of as part of the last year of my PhD and so far the first year of my postdoc. And so this is work that I did as a graduate student at UC Berkeley, as an intern on the Google Accelerated Science team, so at Google, and then I'm continuing on doing at Berkeley National Lab, where I currently hold my postdoctoral fellowship position. And so you'll notice there's sort of a couple titles going on here. The one that was advertised is Euclidean Neural Networks for emulating ab initio calculations and generating atomic geometries. I will be talking about these applications, but I'm also going to dive into the motivation behind why did we go to the trouble of making our own type of neural network layer? Why might it be of interest to a variety of physical applications and how it works? So kind of like the tagline of Euclidean Neural Networks, rotation, translation, permutation, equivariant, convolutional neural networks for 3D point clouds, I thought that might scare away some of the people I most wanted to come to this talk, namely people who are working in the physical sciences that want to speed up maybe their simulations and calculations or enable new capabilities in their field by using a neural network that's really custom tailored for their application. So I hope you don't mind the mild deception of the title, but so there will definitely be a discussion of the applications, but I also want to dive into the details of how these things work. All right, so without further ado, first let me give you a bit of background as how I got into this whole field of deep learning. So my background is that I'm a computational materials physicist. And what that means is given an atomic structure, so where the atoms are, so in this case this is silicon in its unit cell. It's kind of a funny picture of it, but this is in fact silicon, and if you tile this box in 3D space, you get what silicon looks like if you zoom down to the atomic coordinates. So what I did is I would use quantum theory and supercomputers, so basically solving this deceptively simple equation that's actually not so simple. And I would solve those equations using density functional theory specifically to figure out where the electrons are. So in silicon, they're nestled right between the silicon nuclei, right there. It's a covalent bond. And also what they are doing. And so this diagram right here is the not so intuitive band structure diagram, or affectionately called the spaghetti diagram, because it is relating the energy and momentum of electrons in a crystal, but momentum in this case, because this crystal is periodic, it gets complicated. And so instead of using numbers like a normal plot, we use these Greek letters and stuff. But what these diagrams basically tell you is that if the bands are very curvy, the electrons can move around very easily. If they're flat, the electrons can't really move around. And then the gaps between energy levels tells you how much energy it takes to go between one level and another. So, but essentially what I was doing for most of my PhD was, given a structure, calculate the properties of that material. But there are many things that we might want to do with this information. So what I want to do is I would like to use deep learning to speed up these calculations. So I mentioned I have to use quantum theory and supercomputers. These things can take anywhere from minutes to hours to weeks to years to run these calculations. So I'd like to be able to do that faster. So maybe deep learning can help with that, to emulate my quantum mechanical calculations. I would like to propose new structures. So when I have a DFT calculation or any sort of quantum calculation that I want to do, I need to give it a starting guess, a good structure that kind of makes sense. But I'm only limited by sort of the bag of structures that I have. So I'd like to be able to generate new ones. Even more than that, going from structures to properties is well and all, but what I really like is if I can have a laundry list of properties that I want what are the structures that are going to give me those properties? And what are structures that I can actually make in the lab? So this is called inverse design. So that's what the blue arrow is. And then furthermore, I want a way to make sense of all these relationships. So I don't just want to be able to go back from structures and properties. I would like a map that kind of tells me where am I going in chemical space and what's that going to get me property-wise. So I want to use deep learning for all these things. And the question comes up, what types of neural networks are best suited to these tasks if we do want to use deep learning for them? All right, so before I dive into that, because I think we have a very broad audience, I'm not going to assume you know what a neural network is. So let's talk about that. So I'm going to give a brief primer on deep learning, which uses neural networks to do amazing feats of image recognition and self-driving cars and machine translation. So deep learning is a specific subset of machine learning, which itself is a specific subset of artificial intelligence. And a model, or the neural network, is simply a function with learnable parameters. It takes some input x, and it gives you output y. So now I'm going to write down probably one of the simplest neural networks, and it's by this equation. So we have some input x, let's say it's a vector. We have learnable parameters w and b. W is a matrix, and b is another vector. We're going to apply w to x, add b, and then we're going to add a nonlinear function. So I've picked hyperbolic tangent, but it could be your favorite nonlinear function like a ReLU, which is simply an element-wise function that if your number is less than 0, it's 0. And if it's greater than 0, it's the same thing. So this is just the simplest example of actually a totally bona fide, fully connected neural network. And then I'm showing it below sort of in a diagrammatic approach that I'll use for the rest of these sort of slides. So we have a linear transformation and an element-wise nonlinearity. Oh, also, I want to emphasize, the goal of my talk is to be understood. And so if at any point I am saying something confusing or unclear, I highly encourage that you ask me a question. I don't need to get through all my slides. I know what it's going to say. But if I would much rather prefer that I say something useful for you that's going to enable you to do great science things. So I just wanted to interrupt and say that. OK, fully connected neural network. This is what 2 layers look like. We've simply added on more functions. We've added on more layers with the general principle that neural networks with multiple layers can learn more complicated functions. The concept of deep learning is that by going deeper, oh gosh, before I go on to that, you've probably seen this diagram. I don't like this diagram because I think it's very confusing. But this is also probably, if you've seen talks on neural networks, you've probably seen these diagrams of neurons and inputs and outputs. As a physicist, I much rather prefer the equation. So I don't know which one is best for you. They're both equally good explanations, but I just wanted to put a shout out that this is an equivalent description of these type of neural networks, of having numbers flow between nodes and having operations acted on them. I added this last minute, so I wasn't expecting it. OK, any questions from there? Or else I'll move on. Looks good. OK, so deep learning is the idea that you can learn richer and richer representations of your data, or more interesting and complicated things, by adding more layers. So this is what deep learning is. OK, people will often talk about deep learning needing lots of data. The reason for this is often models of the most common types have like millions of parameters in them, and you don't want to easily overfit. So you want to give it lots of examples to learn from so it can learn the most general model that's possible from your data. The next ingredient that's crucial for deep learning is your cost function. You need to evaluate how well your model is doing through this training process that I'll talk about a little bit more later. You need a metric to assess how well it's performing. This is synonymous with calling it the loss or the error. And it's going to show up in the next thing, which is sort of the magic sauce of deep learning, and that's how do you update the parameters in your model? And this is the big insight for deep learning, is that you construct a model that is differentiable, meaning literally you are able to take derivatives of your model with respect to every parameter in your network. So you're able to attribute blame, saying this parameter is the reason why my loss is higher, or this parameter needs to go up or down. And so the easiest way to articulate something that's differentiable is to use a framework called differentiable programming. So if you've heard of TensorFlow, PyTorch, maybe some of you even use JAX, which is a really cool framework. This is one of the easiest ways to construct a differentiable model that you can flow gradients through to update your parameters. And so this loss, we take derivatives of the loss with respect to all these parameters, and that's how we update the parameters. This is called backpropagation, which is sort of the computer science term of the chain rule for those of you who've taken calculus. So that's kind of the magic sauce of how this works. Last but not least, so I was showing you dense neural networks beforehand of just matrices acting on vectors. There's another type of very popular neural network model that's relevant to Euclidean neural networks because basically we're based off of these types of neural networks, and these are convolutional neural networks. And these act on images, and you have a kernel that you essentially is like a filter that you scan over your entire image, and each time you do that, you're doing an element-wise multiply with the image underneath. You sum all those numbers, and then you get a new image. Okay, so this is one picture of it where the yellow is the filter, the red numbers are the specific numbers in the filter, and this is showing what happens when you do an element-wise multiply. And then this is what it kind of looks like if I take this edge detector filter and apply it to an actual image, just to show you what the output looks like. And that output is what goes on to the next layer in your network. All right, so any questions on that? That's just kind of give a very broad overview of the different mechanics in neural networks. All right, good to go. So back to our original problem, what types of neural networks might be best suited for these tasks? In my case, for computational material science, maybe in your case for something else. So I want to tell you a little bit more about neural networks. So there's a lot of assumptions baked into neural networks that maybe kind of go unseen because we kind of take them for granted as like this is the standard way that you do things, but there's actually a lot of assumptions baked into them. And assumptions about the data type that they traditionally act on are encoded into the network operations. So again, let's take into consideration dense networks. And in this case, red is going to represent your input, and blue is going to be like your learned operation or your learned layer. So in the case of dense neural networks, we have some input vector. We have a matrix acting on that vector. And what we're implicitly assuming is that worst case scenario, the numbers in your vector are completely unrelated. They're independent. They're telling me orthogonal different aspects of your system. So worst case scenario, this network can handle that. So that's kind of a good thing to keep in mind. They're not assuming any correlation between these different components. Even if there is, they usually can work out very well. Okay, so back to those convolutional neural networks. The assumption here is that rather than having tons and tons of parameters connecting each input and each output, you use a filter to emphasize the importance of locality. That in this case, if I have an image, pixels close to me are more important than pixels that are further away. So there's this sort of geometric locality. Furthermore, it also implies that these features that you want to detect can be found anywhere in the image. And these are assumptions that are just baked into the operations of a convolutional neural network. Any questions on that? Okay, last but not least, and certainly not exhaustive, let's say you have sequential data like text or sound or anything like that, and you might use a recurrent neural network. And in this case, you have basically an assumption that the inputs and outputs depend on what has come before. So that I need to know something about what has happened in order to make my prediction. And so you'll end up having multiple inputs and also passing processed information through that part of the network. So then the question is, what are our data types in materials physics, and what are the neural networks that can appropriately act on these data types? So I'm going to flip it by saying, what assumptions do we want built into the networks? And I'll give two examples of the types of things that I wanted in my neural networks that I didn't find out in the wild and had to make to solve this problem. So let's say you have some sort of atomic system, whether it be a crystal, molecule, protein. Atomic systems form geometric motifs, so little patterns of atoms that can appear at multiple locations and orientations in a given example. So here I'm showing a rubidium manganese chloride crystal, and they have these octahedral motifs. So you have, I believe it's manganese that's octahedrally coordinated by chlorine atoms. And you'll see these two examples are in different orientations. It'd be really nice if my neural network knew that those are the same thing. They're just in different orientations. So I would like for it to understand that just because I rotated something doesn't change sort of what it is, whether it be a simple motif or a molecule or anything bigger. Furthermore, the properties of physical systems transform predictably under rotation. So let's say I have this toy example. I have two masses, and they have velocity and acceleration vectors. Now, if I rotate my system, the masses stay the same. If that wasn't the case, that would be like the hit weight loss program in LA or something like that. You rotate and look, you're thinner. So no, masses are sadly scalars, so we can't use any rotations to change that. But velocities and accelerations are vectors, and so they do change with the rotation. So I changed my coordinate system on the bottom, and you can see that the masses didn't change, but the velocities and acceleration vectors do. So what does this mean? This means that our data types are geometry and features on that geometry, or geometric tensors, which are specifically features that transform predictably under rotation. And I'm going to emphasize that I'm going to say geometric tensor to specify these types of tensors. If you use TensorFlow or PyTorch, they also call those tensors. Those are really multidimensional arrays, versus geometric tensors have this specific transformation properties. So these two data types actually imply something really significant. And the assumption is that the systems we are considering have Euclidean symmetry, meaning that the laws of physics don't change just because I moved 5 steps to the left. And it doesn't change if I'm oriented in a different orientation. Now, given that we have gravity, the symmetry's broken, gravity's pointing down. But if I was just in 3D space, these things would be the same. And then additionally, inversion. So if I swap my coordinates from x, y, z to negative x, negative y, negative z, the laws of physics act the same under inversion. All right, so here's an outline for the rest of the talk. So I'm going to give a brief overview of what neural networks with Euclidean symmetry can do. Then I'll talk about how these things work and some applications. So what are some things that they can do? Well, let's say you have a bunch of 3D Tetris shapes. These are, in fact, all the unique ways that you can stack 4 blocks in 3D space. And interestingly, 2 of these objects are chiral, meaning that they are related via inversion symmetry. So you can look at the radial distances between them, and it's the same. You can only distinguish it using angular information. So let's say I show my neural network these shapes one at a time, encoding them as 4 points in 3D space. So I give them 4 points in 3D space, and I say, please tell me which shape this is. So if I've trained it to identify those top pieces by a guarantee of how the network is constructed, by default, I can perform the same task on this test set of rotated objects, and it should perform perfectly, even though it's never seen a rotated Tetris piece in its life. This is what it means to have rotation and translation equivariance. I can show it the same thing in any location or orientation, and it knows it's the same thing. And it also knows that it was rotated or translated. Okay, here's maybe a more practical application than Tetris pieces. Given a molecule and a rotated copy, let's say I want to predict forces on that molecule due to it not being in equilibrium. The predicted forces will be the same for the original copy and the rotated copy modulo a rotation. So the forces will rotate with the rotation of the input. So that's nice, because guarantees are nice to have if you're doing molecular dynamics. Little errors can add up really fast. Okay, and then another thing that's close to my heart as someone who deals with crystal structures, again, this is silicon, showing yet some more unit cells that are possible for silicon. So to these networks, they're primitive cells, which is like the smallest way to represent a crystal, conventional unit cells, the ways you normally show them, and supercells, which are basically bigger versions of the same crystal. They also contain the same information. These networks can look at these types of inputs with periodic boundary conditions, and it will produce the same outputs. It understands that this is the same thing. You're just showing me a bigger version, and all the outputs will transform accordingly. Okay, so what's the magic sauce? How does this work? I'm going to give an overview. What are the inputs and outputs of this network? What are the operations? What do the filters look like? And then how do we, kind of a deeper dive into what these inputs and outputs really mean? Okay, so we start off with a traditional convolutional neural network like you should for the images, except for we don't want to deal with images because images of atomic systems are sparse and imprecise. If I show you this image of benzene, there's a lot of dead pixels that really aren't doing much, and worse than that, it's going to be less precise than if I just use points. So first of all, we use continuous convolutional neural networks. So meaning instead of a discrete filter, we're just going to evaluate a continuous function, which is that slide. So you have a convolution center, you have some radial distance vector, you evaluate some function for that radial distance vector, and that's the filter that you apply to the system. But last but not least, we have to encode the symmetries of 3D Euclidean space, so 3D translation, so moving things and rotating things. And just to be a little bit more specific about what we mean, let's say I'm classifying images of bunny rabbits. If I want to identify a rabbit in one part of the image, if my network has translation equivariance and I can identify that rabbit, I can definitely identify the rabbit if it's been moved. And let's see if okay, yes. So convolutional neural networks have this baked into them because of this assumption that you're using the same feature kernel, or you're using the same filter on all parts of the image. So that part's already built into convolutions as an operation. So that's great. But what about rotation equivariance? If I have a rabbit and I have a rotated version, I don't have this guarantee that it can learn, that it automatically understands both. So the way that people have traditionally solved this problem is through either data augmentation, I just show my network a bunch of rotated rabbits, or I can make a network that is rotation invariant. So I'm only using information that doesn't change under rotation, such as radial distances. So if I have a network that only operates on radial distances, those don't change under rotation, but I'm throwing out angular information. So ideally, we want a network that preserves both the geometry, so we want to maybe keep the geometry through the network, and exploits still the symmetry of rotations. So another thing I want to bring up is that several groups actually converged on these ideas at a similar time. Our paper happened to be first, but this has actually been a very rich field that it's been developing over many times. So I want to give a shout out to some of the really important contributors to this. So there's our paper, Tensor Field Networks, which is what we originally called our version of the networks, but then Clebsch-Gordon networks came out from Risi Condor et al. And then 3D steerable CNNs came out from folks in Amsterdam with Taco Cohen and Mario Geiger, a good friend of mine. So a lot of this stuff sort of came together around the same time. So when I went to NeurIPS in 2018, I said, you know what, I need to go meet these people because this is great. There's other people out there working on this and that care about this. So I met up with Mario, and we started talking about code. And there were certain things about my code that I liked, certain things about their code that I liked. And it's we should just be in the same repository. So we were coding at NeurIPS, merging our repositories. And so now tensor field networks and 3D steerable CNNs, which ours worked on points and theirs worked on images, but the underlying math is the same. We decided to merge into one repository, and that's what we're calling Euclidean Neural Networks. Any questions about that? All right. Okay, so just to reiterate again, and let me just see, how am I doing on time? Great. Okay, perfect. Okay, so to be rotation equivariant, because the rotation equivariance thing is kind of the gnarly thing that we had to deal with, translations was already baked into convolutions. Just want to reiterate again, to be rotation equivariant means I could either rotate my input, so I can either rotate my molecule and put it into the network and get the output forces, or I could put in my unrotated molecule, get the forces, and then rotate the forces. So this is what it means. I can apply these rotations anywhere. Now, we don't, in practice, apply these rotations. It's just more of, in theory, if I have two copies and one of them's rotated, it's the same as if I just put one through the network and then rotated the outputs. Yeah.
So that's more broad than the case that you had with the Legos, where you're saying it was the exact same answer.
Yeah. Yes. Yeah. Yeah, it's much stricter, actually. Yeah, and this brings up kind of a philosophical thing that I've been thinking about lately. So let's say you have a network that can do this. It predicts the right forces regardless of the orientation. But inside the network, it's doing magic goop stuff that doesn't actually obey these symmetries. Do you care? Yeah. And so I think in a lot of science, so in a lot of industry cases, you don't. You just care that it got the right answer. But in science cases where we might want to interpret our networks, the fact that it's doing the right thing fundamentally at every single layer is super important. So yeah, awesome. I'm really excited that you brought that up. Okay, yeah, so this is true at every single layer. So any intermediate representation of your network has this property, and that can be super useful depending on what information you want to get out of your network. All right, so what about inputs and outputs? Okay, the input to our network is geometry and features that live on that geometry. So again, using our toy example with masses and velocities and accelerations, this is some of our data, but we have another layer of organization. So we organize our features by how they transform under rotation. So let's say I have a scalar that doesn't change with rotation. That means it sort of has an angular frequency of 0, because if I change my coordinate system, it doesn't do anything. Versus a vector, if I rotate my coordinate system, it rotates with the same frequency. Now, higher frequencies, it might at first be a little unintuitive to wrap your head around, but it's actually very natural. Consider a polynomial like x times y. if I change my coordinate system, not only is that x changing, but that y is changing. And so you can get things that have like higher frequency change. It's going to be changing with twice the frequency of the rotation. And so that's how you can think of higher level things. But then relating it to like physical data, so let's say you have a 3x3 matrix, you can actually break that up into different, to components of different angular frequency. The trace of a matrix doesn't change under rotation, but the anti-symmetric components change with the same frequency as rotation, and then the symmetric components, which are kind of analogous to like x times y, x times z, and these kind of polynomials, those change with twice the frequency. So you can always take like a Cartesian tensor that you're used to dealing with in continuum mechanics or something like that, and transform it into this frequency representation. They're just different bases. So in this case, our masses have angular frequency 0, and then our velocities and accelerations have frequency 1. Any questions about this? Because this is like usually the part where that's kind of like not as intuitive. Exactly, yeah. So if you rotate a scalar, so if you perform a coordinate transformation, your scalar shouldn't rotate. Now you can have like a pseudo-scalar, for example, and that sort of thing. I think it's but that's if you have inversion. So if I inverted my coordinate system, my scalar should flip sign. So there are these like more exotic like pseudo-vectors where if you invert, then it doesn't change. But that's because of parity. That's because of inversions. Does that answer your question? Maybe not. Well, here, let me try a different example. If I have a carbon atom, it's still a carbon atom no matter how I choose my coordinates. It's not sensitive to coordinate transformations. So it's just a kind of more of a fundamental property of that object that just is not dependent on the coordinate system. Is that a bit better? Okay, any other questions?
Is it like a mass of like an atom or?
Yeah, a mass is an example of one that's a scalar. Energy is a scalar, so it doesn't depend how you change your coordinate system. Energy is a scalar. But you could have vector fields. Like if you have a vector potential for magnetism, then you have a vector field. Or electric fields can be represented. If you have an electric field, that can be vectors, but the scalar field representation of an electric field would be a scalar. So just some other examples. Other questions?
One more question.
Yeah.
So I think I understood your explanation of things beyond the vectors.
Yeah.
And having some value 2 or higher than
Right, yeah.
the rotation. I don't quite map it onto the 3x3 matrix.
Yeah, that's super not intuitive. No, it's like, I didn't quite believe it until I actually worked out the math myself. So I have actually a Jupyter notebook to show you this, but I would probably show you offline if that's okay. Yeah, but no, if that's not intuitive, I don't blame you. It wasn't for me for a long time. Okay, so we were talking about the inputs, but what about these convolutional filters? So it turns out that we use convolutional filters that are also built from functions that have a specific angular frequency. And since we're dealing with 3D rotations, these are the spherical harmonics. And I'll show a picture of them in the next slide, but I just want to first explicitly show, if you don't have symmetry baked into your network, you just have some filter function W. I haven't told you anything about W. All I told you is that it takes in some radial distance vector R. Now, if I have rotational symmetry, then what I have to do is I actually split up my filter function into 2 different parts. A radial component, so just distance information, and an angular component, angular information. This is super analogous to when you're solving for the hydrogen atom, for those of you who have gone through that process, where you end up splitting your function into the part that's radial and the part that's angular. Very similar intuition. Okay, and then I'm going to move on to showing spherical harmonics, but any questions on that? Yeah.
I was trying to catch your description of the convolutional filters.
Yeah.
With these radius.
Oh, yeah. Okay. So when you have a filter for like an image convolution, you're moving it over space. Now, in our case, we don't have a grid. So where do you center the convolution? So you can actually choose whatever you want. What we tend to do, and this is sort of a physically informed kind of bias, if you will, is that we're going to do it from the atom center. So when I'm evaluating my convolution, I'm sitting at a specific atom, so my green atom here, the convolution center, and I'm looking out to my neighborhood. And I'm going to say, okay, I have this radial distance vector, this radial distance vector. So I'm going to apply my filter on this, apply my filter on this, apply my filter on this, combine it with the features that are on those sites, sum it up, and continue forward. And this is very analogous, and I'll go into more detail about the math behind that.
And your radial distance vector is the distance between this atom to the next atom.
Exactly, exactly. That R vector is exactly that. Great question. Thank you.
When you say forward, do you just mean picking any bonded atom, or?
Oh, when you say moving forward, okay.
Or are you going deeper into the network?
Okay, yes. So you actually will do this, and thank you for pointing this out. You do this for every single atom. So there are actually n steps. You don't do them in sequence, like to make it efficient, you vectorize the whole thing. So you do it with just one big matrix operation. But yeah, so moving forward would be the next layer. So you've gotten all the features, you've updated all the features, and then you move on. But yeah, you do have to first do that for every single atom in its environment. Another question? Yeah.
Yeah, that actually, I think, partially answers if you could elaborate. So how are you actually to apply similarity in any particular structure, model, or relationship? Like if it's
Yeah.
categorizing the types of bonds and the structure.
Yeah, so usually we just give coordinates. So we don't really give atom type information. So we're not really baking any chemistry into these networks, which hopefully makes it more general. But what we are encoding is like the radial distance vector. And so if you have similar vectors, even modulo rotation, it's going to be able to see that from how it interacts with the filter. I don't think I'm really answering your question, but I think it might be answered in some of the next slides. So, but feel free to bring it up again if you are not satisfied. Yes?
So there's a very intuitive, like, convolutional center for your first layer.
Yeah.
After your first layer, it becomes a lot less intuitive. You can't just, like, convolute over atom positions. How would you go about that?
Yeah, so in this case, we actually do. So yeah, this is a choice. So we only store features from our convolution on the convolution centers. So we only store features on the atoms. But you're totally right that that doesn't necessarily need to be the case. You could start with points, and then you could update features on a grid. Let's say you're interested in a charge density and you want to do it on a grid. You could do it. There's many ways you could do it. So that's a choice. And for a lot of applications, just keeping the information on the atom centers is sufficient. But there might definitely be a use case where that's not the case. Okay, great questions. Cool. Okay, spherical harmonics. These are my favorite functions. I don't know if it's Stockholm syndrome or what, but so these are the spherical harmonics. They might look familiar to you because, as I mentioned, they are the angular portion of the hydrogenic wave functions. So L equals 0 are your s orbitals, L equals 1 are your p orbitals, and L equals 2 are your d orbitals. Now, what I'm inscribing underneath them are basically what are these functions proportional to? So these are functions that take in angles. So what angle are you on the unit sphere? And spits out a number. And so what I'm plotting here, these shapes is sort of the radial distance away from the center. What that's indicating is the magnitude of the function at that angle. Plus is positive and minus is negative. Here I'm showing the real spherical harmonics because it is simpler to describe. But there are also complex versions of the spherical harmonics that are equally expressive. So L equals 0 is constant. It doesn't change depending on where you are on the unit sphere. L equals 1 is proportional to y, z, x. I'm going to emphasize that they are in that order by convention. So if you wanted to have an L equals 1 output and you're predicting x, y, z, you're going to be convinced that the network's not equivariant, but I promise you it is. And it's just that you have to permute these different things. L equals 2, it starts getting a little bit more complicated. So you have these kind of polynomials like x, y, y, z, z, x, and then you have these weird combinations of like z squared minus x squared and these sort of things. The reason for that is because x squared plus y squared plus z squared equals r squared. And that's actually a redundant degree of freedom that you can just kind of subtract out because that's equivalent to L equals 0. So that's what these things are. The fancy version of what these functions are is that they are the basis functions of the 2L plus 1 dimensional irreducible representations of SO3. That's the real reason why we're using them, is because these functions transform beautifully and simply under 3D rotations. So that's if you're Google searching these terms, but I think just thinking of them, these are functions that kind of travel together under rotation. And what I mean by that is that, like, let's say I have spherical harmonics of a given L. I have some linear combination of spherical harmonics. In this case, this is L equals 1. So I have these combinations of the y, z, and x spherical harmonics. And let's say I change my coordinate system. I do a rotation g. G is the name of my rotation. I have a function D. It's called the Wigner D matrix. And I'm not going to go into too many details, but its shape, it's just a regular matrix that's 2L plus 1 by 2L plus 1. So it's a matrix that'll transform one set of spherical harmonics to the rotated set of spherical harmonics. So if I had L equals 2, it's a 5 by 5 matrix. For L equals 1, it's 3 by 3. And the cool thing is that my new function in my new coordinates, it's still the same angular frequency. The frequency didn't change. What did change are the relative contributions of the different spherical harmonics of that angular frequency. And so this is really why we're using this basis, is because if we keep everything organized by L's, then we can easily kind of like divide everything up. We know what things are interacting with what. It's a very convenient basis because we're using spherical harmonics for our filter functions, and we're using the same representation as our input. Any questions about that? Okay. This slide is not meant to be comprehended. It is to evoke fear and terror into the hearts of anyone who's taken second semester quantum mechanics. If you've seen this table before, this is where it shows up. So, okay, let me explain why I'm even showing this picture. So features and filters in our network are not simply scalars. We just went through this whole thing of talking about how certain L's will transform differently under rotation. And so our filters and features, now we can't just multiply them together because we don't have scalar multiplication by our side. We have to do something a little bit more complicated. So we have to use something called tensor products. And because we're dealing with geometric tensors, a tensor product can actually be simplified using the Clebsch-Gordon coefficients. And for those of you who have experienced the joys of Clebsch-Gordon coefficients, it is in fact the same math is involved for the addition of angular momentum. And so if you have used chapter 4 of Griffiths, this shows up there. But let me more maybe intuitively explain what is going on with the tensor product and these Clebsch-Gordon coefficients. Okay, here's an example of a tensor product. Let me combine a scalar and a vector. Easy. I just get another vector. It's either bigger or it's smaller, so it's been scaled. Okay. But if I have two vectors, it's a bit of a different story. There's many different ways you can combine two vectors. I can basically assess how similar two vectors are by performing a dot product. This gives me a number. This gives me a scalar with, frequency, angular frequency 0. I could perform a cross product, so I can get two vectors and get another vector out. I could also perform an outer product, so I can get two vectors and get a matrix. And as I said before, this transforms in a little bit less intuitive a way, but it actually transforms as L equals 0, 1, and 2. So the tensor product embodies all these different operations kind of in one go. And the Clebsch-Gordon coefficients are basically telling you if you have something incoming of L equals 1 and you have something two incoming inputs as L equals 1 and L equals 1, what angular frequency outputs are you going to get? So it's basically just a projection. How do I take two indices and combine them into one? Any questions on that? Cool, awesome. Okay, so what changes in our convolution due to this? So in a scalar convolution, you have your filter function, you put in your radial distance vector, and then you multiply it with a scalar multiplication times whatever's living on that point that you're convolving over, so the input. And then you get some output, where your filter is basically shuffling between, I have input channels and output channels, and I'm just going to convert all your input channels to an output channel. Okay, so what changes in a geometric tensor convolution is that you don't have scalar multiplication, you have this tensor product. And inside this tensor product, which I'll show in the next slide, you have your filter channels, you have your input channels, and then you combine them with this tensor product into totally different channels. So it's not just I, J, I to J. You have I, you have J, and now you have K, which is something different. And so those are the main things that change. So kind of illuminating a little bit on this, so using our example, let's say I have an input of L equals 1. I need to apply some filters, and I want an output of L equals 1. So there's specific selection rules for determining which L filters or which other L's you need to go from one to the other, and these are called selection rules, and I've written them down here, but feel free to completely ignore it if you don't necessarily want to read that. What I'm showing here is that, okay, we're going from an input L of 1, which has 3 different channels, to an output L of 1, which has 3 different channels. And so what I wanted to do is show that, okay, we have filters that are L equals 0, L equals 1, and L equals 2. And I wanted to show them on that 3 by 3 matrix to kind of show where the different filters are going to contribute for mixing the YZX of the input to the YZX of the output. And so this is just kind of to show a picture where those spherical harmonics show up. Okay, good. Oh, well, that's like, yeah, okay, good. So this is just a GIF to kind of show you what a randomly initialized radial, or these filter functions might look like as you're moving with varying L. So it's mainly just to kind of look interesting, but it's R equals 0 when the spheres are the only ones that are there. Okay, I'm going to speed up just a little bit on this one, but I'm happy to come back to this. So as we discussed, different numerical features, you can interpret them as energies or forces or matrices, tensors, things like this. But the thing that I'm really excited about, and I think that these networks are going to be like kind of especially useful for, is that you can interpret the inputs and output features as geometry. You can literally just plot what these spherical harmonic signals look like. So this is a randomly initialized network where I've just put in trivial features on a tetrahedron with a center, and this is the output. If I have it output spherical harmonics up to L equals, I believe, 5. And so you can see like they're highly symmetric. There's a lot of things going on. It almost, it already kind of looks like electron orbitals might look like this just due to the symmetry of the problem. And what's really cool about this is that using these using this as a geometric picture, you could imagine placing points on the maxima of these functions. And this is actually a permutation invariant way of generating new points. So you're not assuming any order to this new points that you're generating. You're just putting them out there. So you can output highly symmetric objects in one go. And I think this would be useful for generating atomic geometries. Another point, which this one's a bit subtle, so I might go a little bit faster on it than I would like to, and I welcome questions at the end. Okay, this is a very weird feature of the networks that we only realized this summer. The outputs of the network have to have equal or higher symmetry than the inputs. And there's 2 tasks that I can demonstrate this property with. So let's say I have 4 points representing a rectangle, and the task is to deform that rectangle to a square. Now let's take the task and flip it around. Take a square and make it a rectangle. What I'm going to show you is that we can do 1, we can't do 2. But we also don't necessarily want it to do 2 because that's breaking symmetry. Okay, so I'm going to show with these blobs, these spherical harmonics that we're interpreting as geometry, as to where the blue points want to go. They want to go to the orange point. So this is showing that the input is just the coordinates of the rectangle, and then the blobs are just the geometry that we want to displace to. So the fact that it's overlapping with the orange means it's doing the task. So we're able to do this one, and you can do this in like less than 100 training steps. It's really fast. Here's task 2. Let me explain what's going on. So it wasn't able to do the task, basically because you're asking it to deform to a rectangle in a specific direction. And so it's not able to do this, and so the best thing it can do is it can output the degenerate options given its symmetry. Well, it's like I could have gone over here, but I could have also gone over here. You didn't really specify the problem well enough for me to actually make an informed decision. And so the network can't train. It can get to a certain level, and then it can't go any further. Now, I argue this is actually what we want it to do because this actually happens in physics. So what's going on? I'm putting some numbers up here, which are just the point group symmetry. You can ignore those, unless you're comfortable with that. But basically what's going on is that going from a rectangle to a square, we're going to higher symmetry. A square is a much higher symmetry object. But going from a square to a rectangle, you have to tell me a bit more about space. You have to break the symmetry of the square in order to determine which rectangle, because it could have been this rectangle or it could have been this rectangle. Okay, so we can actually modify the second task and do square to rectangle with symmetry breaking. And what we're going to do is we're actually going to add just some very little piece of information and anisotropic information on each point. What we're actually going to do is we're going to add a component in the x squared minus y squared spherical harmonics. So this is just a single entry of this input to this network. And just by adding this slight anisotropy between, like basically saying x is different than y, it can learn the task perfectly. So it'll look exactly like how it was looking in task 1. So this is super non-intuitive, it's subtle, but it's a really cool thing. And the key thing that I want to point out is that we actually want it to do this because physics plays by the same rule. It's a very deep and interesting topic. Maybe I just think so, but I think a lot of physicists think so. Physical processes have to choose energetically degenerate options in order to break symmetry. And if you set up like 100 identical systems and they have to break symmetry, they'll choose all of the options with equal probability. So if I had to choose this rectangle versus this rectangle, you'll get half the population choosing one and half of it choosing the other. So that's kind of cool. Okay, applications. We have like 3 minutes. We can talk about it. Okay, yeah, so it was certainly false advertising on the applications of these networks, if I'm going to talk about them in 3 minutes. But hopefully you're highly motivated to learn more. Okay, things you can do. You can use these for ab initio molecular dynamics. So you can take high-quality quantum mechanical forces and train them to be very fast so that you can actually use them in a practical molecular dynamics setting. So I have these really wonderful collaborators at Harvard, Simon Batzner, who's done so much heavy lifting on this, and Boris Kaczynski. So they presented this at APS March meeting this past year. And so what they're doing is they're using these networks to directly predict forces on these molecules. Previously, what people do is they predict an energy and take gradients of the network to predict forces. So it's an additional step. And they showed that you could do this on the MD17 data set, which are molecular dynamics trajectories of these specific molecules. So that's cool. I have some good friends at TU Berlin who just put this awesome paper out. It's a Nature Comm paper, where they're basically using networks to predict the Hamiltonians of small molecules with very high accuracy. And then from there, you can also get wave functions, charge densities. Super cool, great paper, recommend reading it. Problem is that their network is not rotation equivariant, so they did have to train with augmentation. And in this case, one of the molecules they're doing is water. And so you actually have to show it many different distorted versions of water in different orientations for it to learn it. So my intern this summer, Mario, we said, well, why don't we see if we can actually do this with a rotation equivariant network, so we don't need the data augmentation. So this is what Mario is working on. And this is just to show you, so with Euclidean neural networks, we only need to show it one orientation of a given example. So this is just to show you what this Hamiltonian matrix looks like when you rotate it around. It changes wildly for the same exact geometry. So this is sort of motivated as to why it could be really helpful if we don't have to learn all the different orientations. So that's one thing that we think is going to be very useful for these types of networks. Another application, I was talking with my friend Rafael Gomez-Mobarelli. He's a professor at MIT, and his awesome grad student Wuji Wang. They put out this super nice paper for doing autoencoders for coarse graining. So if you do an all-atom molecular dynamics simulation, that can be super slow if you have many, many, many atoms. So oftentimes you simplify the problem by using coarse grain atoms to represent your molecules. And one of the issues that, oftentimes you want to go back to the decoded molecule. And so my awesome intern, Ben, we said, okay, well, let's consider a test problem, because there's one thing. Oh, okay, yeah, oh, this is a school. Yeah, okay. This is what happens when you work at a national lab, you forget about bells. Okay, yeah, so there's two problems in this. There's coarse graining, which is taking many atoms to fewer atoms, but then there's also fine graining, which is taking fewer atoms to many atoms. And so we were kind of curious as to how we could actually maybe help generate the full atom geometries. And so we did a test problem. We said we're going to go from the centers of a bunch of connected tetrahedron to the full atom picture. And what we found is actually, like, this problem is what motivated this whole rectangle square business. It's because we saw this and we were like, what is going on? Why can't it do the task? So here's what happens if you train the network to try and predict where the full atoms are if you're only given the centers. And what I want to point your attention to is that it's not working. Most importantly, let's see once it goes back. So when it gets in the elongated position, I want you to notice that they're radially symmetric outputs. And this is because in the case where you just have an elongated chain, you have rotational symmetry. So it can't give you blobs in a specific direction because, well, you didn't give it that information to begin with. And so what we're finding is that by adding very principled symmetry breaking, and sorry, these are out of phase, but basically you can see that it's doing better. So it's not overlapping just because that would visually be a little bit clunky, but you can see that it's doing a much better job doing this prediction task. But to do this, we had to break symmetry, so we had to give it a little bit more information. Last but not least, this is the thing that I'm working on, when I am at my desk and